In section 2.9, we're going to talk about differentials and linear approximations. What we would like to ultimately do in this section is to be able to approximate the value of a nonlinear function using a linear function, that is using a straight line. Before we actually do that, however, let's begin our discussion with that of differentials. Okay, so now as it pertains to differentials, our objective is the following. We would like to know how does a small change in independent variable x affects the value of the dependent variable. That's what we want to do in the beginning. But remember, ultimately we would like to approximate the values of nonlinear functions using linear function, that is straight line approximations. So in order to be able to do what we want to do in the beginning, approximate the effect of y, the effect of x on y, we need to know what differentials are. So before we talk about differentials, let's talk about increments. An increment is simply a change in the value of x or y. Okay, that's all an increment is. So for example, let's say I have here's x and y. Suppose I have a function here, and as I move from one point to another point, so let's say initially we are at x here, and this would be, let's say, f of x, and then some unit later, so this would be x, some distance later, I should say x plus delta x. The triangular shape here, this represents delta. And remember the word delta here, think of it as change. Okay, so when we say delta x, that means change in variable x. And this would be x plus delta x. So the distance going from initial point to another point, that's what delta x is. And that's what the increment of x is called. Now, once you go delta x unit over, then this would be f evaluated at x plus delta x, correct? And that's all that is. So delta y, therefore, is the change in y, and delta x is simply going to be the change in x. That's this distance. And that's all increments are. So I'm going to write this now. Therefore, we can write the increment in x. Increment in x is written as delta x, and the increment in y is written as delta y. So that's all those are. So remember, change in x and then change in y. Okay, so let's take a look at an example here. So in our first example, I'm going to make a simple function. Suppose I have y equal x squared. And let's say we're moving from x equals 1 to x equals 2. Now, I did mention delta x is a small amount usually, the differential of x. But here, just for illustration, I'm choosing a large delta x here. So as we go from x1 to x2, we want to find delta y and delta x. Okay, change. In other words, we want to find the increments of x and increments of y. Now on the graph, of course, this is the basic parabola. Let's say this is point at when x is 1, y is 1 squared 1, and you go to 2. When x is 2, we go to 2 squared is 4, right? Okay, so you can see that the change in y, that's delta y, is going to be 4 minus 1, which is 3. And delta x here is a change in x. So our delta x is going to be 2 minus 1, 1 unit. And delta y is going to be f at x plus delta x minus f at x. Means the higher point minus the lower point. Now f at x plus delta x, that's going to be f at 2, and f at x is f at 1. And I already have those on the graph. That's going to be 3. Okay, so there we have it, and that's what these numbers turn out to be. Again, I just want to illustrate the whole idea of delta x and delta y. Now, instead of actually using the actual function here for delta y, because oftentimes that takes time, and we want to find a different way, an alternative way of doing this. So let's talk about differentials, okay? And with differentials, we are actually going to use the tangent line to do what we just did, to approximate delta y, the change in y, the actual increment of y. So here's how our layout's going to be. Let's say I have the following situation. So that same curve that we had before, something like this. Now here's point at some point x, and this is of course f of x. So remember, we go to a point later, and point later that's going to be f at x plus delta x. So we go delta x unit later, and again I'm exaggerating delta x here just so you can see it. That's just for clarity. Okay, usually delta x is maybe this far. You see how far I am from x right in here. Delta x is that tiny distance from x to this line. Okay, but again, I'm for the geometry of this to make sense, I'm using a larger scale here. All right, now if I draw the tangent line at x, okay, the tangent line at x, it's going to look something like that, right? That's going to be the tangent line. And this is what we're going to call t, or the tangent line, okay? Now, again, delta y, we know what delta y is, right? The actual change in y is delta y. That's this distance here, that's delta y. Now, we can see that we can approximate this delta y, right, that change, using the tangent line. So if I use the tangent line, actually, I can say, well, this would be the approximate change in y, wouldn't it? This distance right here, that's what it's going to be. So this distance, therefore, from the tangent line to the lower point f of x is going to be dy. Now, dy is what the differential of y is, okay? Now, of course, delta x doesn't change whether I use the tangent line or I actually go from one point to the next point. Again, what we would like to do is do this. We would like to approximate. We're going to say delta y is approximately equal to dy, particularly if delta x is close to x, right? I mean, focus on this portion. Let's say if this is my delta x now, this distance here, notice the difference between the function and the value of the function approximated by the tangent line. There's not much of a difference there. So that change is going to be very close, right? So here, dy and delta y are very close to each other. Okay, and that's what the differential is. So again, if delta x is small, then dy would be a good approximation for delta y. And that's what we want to do. So now what we can do is actually, if I construct this triangle here and call this angle theta, then we can write the following relationship. We can say that tangent of that angle theta, tangent is the ratio of opposite to adjacent, is going to be dy, which is the differential of y, over delta x, the increment of x, right? Or from this we can say that the differential of y is going to be simply tan theta times the increment of x. True? Now remember earlier when we talked about the derivative back in section I believe it was 2.1, we showed that tangent of theta is equal to f prime of x, right? Remember that work we did? So I'm just going to say from earlier work, I think it was from section 2.1. You can watch that video. that I had earlier for that section. So we're going to replace tangent of y with, because again it's easy even without section 2.1 reference here. This is theta. The rise over run, right? The coordinates of this would be like coordinates of this point are, in terms of unit circle, are cosine theta, sine theta, and this would be cosine theta, this would be sine theta. Slope of a line is rise over run, sine over cosine. That's how you get slope, which is equal to tangent theta, because the ratio of opposite to adjacent, rise over run of the triangle. So therefore I can replace tangent of theta with f prime of x, right, times delta x, and that's the actual value of the differential of y. So we can calculate the differential of y, and that's what dy is called. This is called differential of y, and that's what that is. And we can actually replace delta x with dx in using differential notation. So differential of x is actually dx. We use those right over here. Differential of x and increment of x are the same. So d of x equals a differential of x. And that's going to be equal to the increment of x. Notice there's no approximation there, because that's just the distance, how far you move away from one point to another point on the x-axis. There is no approximation there. The approximation appears in the value of the function that we are approximating. So therefore we can say that dy is equal to f prime x times dx, and that's going to be how the differential of y is calculated. And remember, differential of x is equal to delta x, so we have that established. Now, having done that, let's move on to the next idea in this section. Remember, I mentioned we're going to ultimately be able to approximate the value of functions using straight lines or linear functions. So let's say here's a function. This is f of x. Okay, here's x, there's y. And suppose that you're at some point a here. Okay. And I would like to approximate the value of the function, okay, using a straight line at that point. Okay, so if I draw my again tangent line at this point, right in here, that's going to be the tangent line. Okay, and this line, we're going to call it, like your book does, we're going to call L of x. L here stands for linear. Okay, so we have a linear function that actually attaches to the curve at that point A, right? So what we can do now is we can actually get the equation of this line, right? Because we know what the slope of the line is. The slope of this line is equal to f prime at A, isn't it? Right? That's the derivative of the function by definition, and we can get the equation of L of x using point slope form, right? Y minus y1 equal m x minus x1. Now y minus y1 here, that's going to be y minus f at a. That's what y1 is. Remember, the coordinates of this point are a and f at a, right? Those are the coordinates of that point. And the slope we said is f prime at a times x minus, and x1 is actually a here, right? This is at point x equals a. Now if I solve this for y, then I'm actually going to get move f of a to the other side plus f prime at a slope times x minus a. And this is what the equation of that line is. Okay, So therefore, we can say that the value of the function now, f of x, is going to be approximately equal to the value that is approximated by that straight line, f prime at a times x minus a. And this is what's called linearization. It's called linearization of the function, right? So we're looking at linearization of f at a, of the function f at point a. That's what that is. Again, the idea is to be able to approximate the function, not using the actual change in y, right, delta y, but we can actually do this without going to too much trouble. Now, this approximation is best in the neighborhood of a. Look at the graph I have. So for instance, let's say over here, at this point, call it point B. If I use the line to approximate the value of the function, this is the actual value of the function, right, at B. This is what the approximation is. Look at the difference between them. There is a gross error between the actual value of the function, the higher point, and the linearized value of the function. But if you look at in the neighborhood of a, right in here, the approximation is right on. It's very accurate. So just wanted to point that out also. Okay. And let me remove these extra points here. And so we're good with this one. Oh, that's okay. And that's what we wanted to do. Alrighty. Now, let's take a look at, we talked about linearization. Now let's talk about actually another idea here. Therefore, we can actually write f at x plus delta x, right? We can say that is approximately equal to f of x plus the differential of y. Right, that would be the approximation to the function. Okay, and at point x plus delta x. This up here is actually the linearization. That means you can approximate it using the line. Okay, but this one again goes back to the idea of this one. The one below goes back to the idea of increments and differentials. Okay, and I think we're good. So let's take a look at some exercises here and see how we can employ what we've learned in this section so far. So let me scroll this up, and there you go. Okay, so here's an excerpt from the exercises. Numbers 5 through 14. Let's begin with those, and then we look at other ones. In exercise number 6, for instance, the question is simple. We want to find the differential of the function. That's df. D for differential of the function at the indicated numbers. So for question number 6, here in exercise number 6, in order to find the differential of the function, we need to find f prime of x, right? So f prime of x, therefore, is, you take the derivative, that's going to be 4x cubed negative 6x squared using the power rule. And we want it at x equals 0, right? So there is the differential. And differential of f evaluated at 0, that means f prime at 0 times dx. Remember the formula we had for differential of x? Maybe I should write that here. The formula we had was differential of the function d of f is equal to f prime x times dx. Right, that's what we had from earlier. We had it from up here, right in here. You see that? Okay, and So all I have to do is plug in a 0 for x into the derivative function. That's 4 times 0 cubed, negative 6 times 0 squared. And the whole thing ends up being 0 times. Don't forget the dx here, by the way. It's got to get multiplied by dx. Okay? And we're done with number 6. Again, pretty easy exercise. Now let's take a look at exercise number 12. In exercise number 12, again, this time f of x is x tan x. So for this one, we got to use the product rule, right, to find the derivative. We got to do f prime x dx. True? So first, f prime of x. F prime of x, using the product rule, derivative of first by second plus first times derivative of tangent, which is secant squared. Okay, and we cannot simplify this one, so I'm just going to go right to differential of the function is f prime x dx, and we want this at pi over 4, right? We were given that at x equals pi over 4. And we're going to plug in for x pi over 4 radians. So that means I'm going to have tangent of pi over 4 plus pi over 4 times secant pi over 4 squared. Now remember, that's a 45-degree angle. Tangent of a 45-degree angle is 1. Oh, sorry. And there's, of course, dx. So easy to leave that dx out. Plus, now secant of 45 degrees. Well, secant of 45 degrees. Secant is 1 over cosine, right? And cosine is 1 over root 2, so secant is going to be root 2. That's going to be root 2 squared times dx. And this is going to be 1 plus root 2 squared is 2. 2/4 is 1/2. So 1 plus pi over 2 dx. So we're going to have dx in all the differentials of y's, differential of the function. Let's do number 14, the last in this segment. This time f of x is sine squared x, and we want it at pi over 6. So f prime of x, first the derivative using the power rule, 2 sine x times chain rule, derivative of sine is cosine. And then f prime of x evaluated at pi over 6 is going to be 2 times sine. Remember, pi over 6 now is 30 degrees. So sine of 30 degrees is 1/2. And this cosine is root 3 over 2. These are special angles, so we're supposed to know those. Okay, and there we have it. That's going to be the answer to exercise number 14. Now, let me, oh, and sorry, I keep forgetting that dx, don't I? It's very important to have that dx, folks. There you go. Because we want the differential of it times dx. Let me go one more line here, and that's going to be root 3 over 2 dx. Every one of these will have dx in it, okay, of these exercises. Cool. Now let me grab more of the exercises and I'll attach them here. Okay, let's take a look at now exercise number 18. In exercise number 18, the question asks us for linearization L of x. Remember, that means we actually want to find the equation of the tangent line at a point, okay, which will be used to approximate the value of the function. So the formula we had for, again, linearization of x, we said that f of x is, or for just linearization, sorry, that's going to be y equals to f at a plus f prime at a times x minus a, right? That was the formula for linearization. And now for exercise number 18, all I gotta do is find the derivative. Of course, f prime of x, derivative of sine is gonna be cosine x. And f prime at a is pi over 4, so that would be cosine of 45 degrees, which is 1 over root 2. All right, and we can do the linearization now. So the linearization of x, we can even call it L of x, is equal to f at pi over 4, okay, plus f prime at pi over 4, which we just evaluated, times x minus pi over 4. Okay, and this is going to equal to f at pi over 4, that's the value of the function, sine at pi over 4 plus 1 over root 2 times x minus pi over 4. Okay, and again, sine of pi over 4 is 1 over root 2x. That's just 1 over root 2 plus 1 over root 2 distribute to the parentheses minus 1 over root 2 pi over 4, right, times pi over 4. And let me see, I can, let's also rationalize this, right? Usually we rationalize the denominators. So that's going to be root 2 over 2. And this is equal to 1 over root 2x. And then we can actually factor out here and here. We can factor root 2 over 2. That's 1 over root 2. That makes it 1 minus pi over 4. And we're good with this one. That exercise is done. Exercise number 18. Okay. Let me again get more of the exercises. Okay, now I have more of them. Let's take a look at exercise number 22. In this exercise, in this segment, we actually want to find the linearization of a suitable function. The suitable function depends on what the number looks like. Okay, and then use it to approximate the number. So we actually want to use the linearization to approximate the number. Okay, so let's take a look at number 22. So in number 22, it looks like f of x, because I have a square root, forget the number, isn't that just the square root of x? So it looks like that's the underlying function. Like, what would it be for number 21? So number 21, that's like x cubed. This one is going to be what the square root function. How about this one? That's going to be the fifth root function, right? And so on and so forth. And the last one, of course, is going to be sine x, right? So those are, again, the overarching function, if you will, the underlying function that we need to work with. So in exercise number 22, that's f of x. Now, it looks like if I graph f of x here, that's, let's say, the graph of f of x, right? Square root of x. Here's 0, here's y. We want to find or approximate the square root of 63.8. Well, 63.8, isn't that close to 64? Right? So this is what x is, right? In root x. So it looks like x is 64 here. So suppose this is what 64 is. That's where 64 is. So that's going to act as our a, right? At the point where we actually want to draw our tangent line. So if I draw my tangent line now, there you go. That's what the tangent line looks like. Again, any approximation in the neighborhood of 64 using the green line, this is L of x, the linearization of the function, and this is f of x. It's going to give us good approximation in the neighborhood of 64, but if I get too far from it, then of course the error grows much larger. So how are we going to do this? Let's actually work the formula we had for linearization. Again, what I need to do is do L of x equal, we just did one, is f at a plus f prime at a times x minus a. And this, by the way, this linearization, this form, in second semester calculus, that actually grows into higher order functions. So we may want to use, for example, a second degree polynomial to make this approximation, a third degree polynomial, fourth degree, fifth degree, and so on and so forth. And that gets us into, or it will get you into, the discussion of Taylor series. So this is like, think of this as a mini Taylor series. Okay, the simple case of a Taylor series. So what do I need to do here? I need to find f at a, don't I? So let's do that. F at 64, that's what a is. That means the square root of 64, that's 8, right? That is 8. So I'm going to write this as 8 plus f prime. I didn't do f prime. So the derivative of root x is going to be derivative of x to a half. That's 1/2 x to negative a half, which can be written as 1 over 2 root x, right? And we see this too often, so maybe next time I'll just put derivative of root x is 1/2 root x in the denominator. Okay, now we do need to do f prime, right? We have to do the derivative evaluated at a, that's f prime at 64. That's 1 over 2 times square root of 64. And square root of 64 is 8, so that's 1/16. Okay, so this is going to be 1/16 times x minus 8. And, oh, I'm sorry, not 8, 64. A is 64. Right, 8 is the square root of that, which I did, and there you have it. Now distribute 1/16 to the binomial. I get 1/16x. 1/16 times 64 is -4, so it's plus 8 minus 4, and the final answer is 1/16x plus 4. So that will be the equation of that line, right? The linearization of x. The green line has that. Okay, so how is this going to help us do this now, right? Well, I want to find square root of 63.8, right? So x, the value at x equal 63.8, right? We want to find the square root of that. The linearization at that point at 63.8 is equal to 1/16 times 63.8 plus 4. Okay, and using a calculator at this point, you will get 7.9875. Okay, now the actual square root on the calculator, if you do square root of 63.8, that number is going to be 7.98749, rounded to the nearest 100,000ths, carried to 5 decimal. Okay, so it's very close, right? Very close to it. And the reason we have such a good approximation, actually 2 reasons. One is that, let me do this. There you go. One is that, let's say this is 64. 63.8 isn't too far away from it, right? That's 63.8. So that's one, because we're very close to A, the point at which we attach the tangent line to the curve. Now the other reason the approximation is right on, I mean, look at that, the error is like 100,000th error. And the reason is because at that point, the curve is itself pretty flat right there. So the curve is flattening toward almost becoming a line. So those are the two reasons that this approximation is so good. Okay, and that's exercise number 22, the one we just did. Let's take a look at another one. Let's take a look at exercise number 24. So in 24, again, we have sine of 0.1, right? Let me write that. Exercise 24, we want to approximate sine of 0.1. Now this time, notice 0.1 is very close to 0. True? So we would like to do the linearization at 0. Correct? That's what we would like to do. So we're going to look at a straight line as it attaches itself to sine x at 0. So the function, again, underlying function, is going to be sine x, and a is going to be 0, right, based on this number. If that number was close to, let's say, 30 degrees or pi over 6, then we do that. So what is f prime of x? F prime of x, derivative of sine, is going to be cos x. True? And the linearization, again, is going to be f at a plus f prime at a times x minus a. All right. And f at 0, that would be sine of 0 radians, that is, would be 0. So that's 0 plus cosine of 0 radians. Remember, x is a real number, so this is in radians. Cosine of 0 is going to be 1. So that's going to be 1 times x, because x minus 0 is 0, and that's just x. So the best linearization of sine at 0 is the line x, 45-degree angle line. Remember, the graph of sine looks like this, and this is 0. So here's the linearization. This is L of x, and this one is sine x. That's of course x, and this is y. So that's what we're doing. We're looking at 0. Okay, and that's the answer to the equation of the line. Now at point 1, we just have to do L at point 1. So we're going to say that sine of 0.1, and again, that's in radians, it's going to be approximately equal to the linearization at 0.1. And that's just x, 0.1. So what is the actual value of sine of 0.1? Let me, radians. Okay, I'm going to do this on my calculator. Sine of 0.1 is 0.099. Rounded is 0.1. It's 0.0998. That's what the actual is from the calculator. Even that is approximation, 0.0998. And what's interesting is, even in the calculator, what the calculator is doing is actually doing exactly what we're doing. It's doing a linearization, except with linearization, you only look at first degree polynomial, right? X. But some calculators, most calculators, I should say, actually use higher order polynomials for their approximation, which makes it more accurate. Okay, again, that's the kind of work you do in the second semester calculus. So hopefully you follow this idea of linearization. And let me see if I can find another exercise here. Actually, this is about as far as we want to cover the exercises in this section. This section also talks about error propagation. That the error propagation is this. Let's say I'm measuring the volume of a sphere, okay? And I want to know if, because the volume of a sphere is 4/3 pi r cubed, easy to remember, right? So I want to know what's the error in measuring the volume if, let's say, the radius is measured within 0.1 of the actual value. So in other words, a 0.1 error of measurement in radius, how will that affect the volume? What would be the corresponding error in volume? So that's called error propagation, how the error spreads, if you will, how it propagates, how it is distributed across variables. We're going to skip that part of it. And with that, I believe we're done with this section.